Hey guys, welcome to video 48. Today we're going to talk about the source follower. We're going to derive the voltage gain and output resistance equations for this amplifier. And really most of this video is going to be on the application of Thevenin's theorem. Now, we talked about Thevenin's theorem explicitly way back in videos 6 and 7. But in those early examples, I only looked at circuits that contained independent voltage and current sources. When we're dealing with transistors, we're dealing with dependent sources, and that makes Thevenin's theorem a little bit more difficult sometimes. So I figured this is a good place for me to introduce some of those aspects of Thevenin's theorem that are important for more advanced applications. And in this case, we're going to be talking about it in the context of the source follower. All right, now on the page here, we've got three different source followers using three different types of MOSFET, the depletion mode, enhancement mode, and the JFET. But all three of these devices have the same AC small signal model, and that's what we're going to be looking at. Next, we're going to derive the voltage gain equation for the basic source follower. All right, so here we've got the small signal model for any of those field effect transistors. We've seen this many times before. I've combined RS and the load resistor into single resistance R'(S). And now I'm going to write the KVL equation going clockwise around this loop. And we end up with 0 equals Vin minus VGS minus Vout, which is GM times VGS times R'(S). Right, now what I really want is an equation for Vin in terms of all these variables, and all I have to do now is solve it for Vin, and I've got Vin equals VGS plus GM times VGS times R'(S). And I could have gotten that by inspection, but I want to again stay very explicit with my derivations here. Okay, now voltage gain we know is Vout over Vin. We have an equation for Vout right here, and now we have an equation for Vin, so let's just go ahead and plug those into this formula, and we've got GM times VGS times R'(S divided by Vin, which is VGS, plus GM VGS times R'(S). And since we've got VGS in all of these terms, we can cancel it out, and that's going to leave us with the voltage gain equal to GM times R'(S divided by 1 plus GM times R'(S). And there we go. There's the voltage gain. We can see it's always going to be less than 1. Sometimes it can approach 1, but usually something around 0.5 or 0.6 is pretty common. And of course, I'm going to leave you with a nicer version of this. So let me clear the screen, get my messy writing out of here. I'll carry this over. And there you go. Now you've got something that's worthy of a screen capture. Now what we're going to do next is determine the output resistance expression for all of these equivalent circuits here. And to do that, we're going to apply Thevenin's theorem. Again, just a little bit of review here. When we do Thevenin's theorem, step 1, we normally determine the Thevenin voltage. We'll remove the load resistance and determine the open circuit output voltage, VOC, across the port we're looking at. Okay, just showing it as a generic black box here. The port is these two terminals. This would represent the source, and this would represent ground in our case. What we would do is determine the open circuit voltage, which is the Thevenin voltage. All right, and then there are two different methods that we could use to find the Thevenin resistance. Method number 1 I'll call the short circuit method. We put a short circuit from terminal A to B. We determine what the short circuit current is, and the Thevenin resistance, which is also the output resistance in our case, is equal to the open circuit voltage divided by the short circuit current. And note the directions here. We're orienting our open circuit voltage A with respect to B, and current flow down from A to B. That'll give us the correct sign for this resistance, because when we've got dependent sources in a circuit, we can end up with negative resistances. And that's an interesting thing that can happen, but it's not going to happen here. Now, the second method for determining Thevenin resistance is to use a test source. All right, in order to do that, what we would do is deactivate all of the independent sources in the circuit. So if we had any normal voltage or current sources, we would deactivate them, replace them with their internal resistance. Then we would apply a test source. We can use either a test voltage or a test current, whichever is more convenient. If we apply a test voltage, we determine the resulting test current. Note the direction of the current and voltage. And we'd find RO or RTH as V-test over I-test. And likewise, if we used a test current, we'd find the resulting voltage drop across the test current source, plug that into the formula, and that would give us our Thevenin resistance, which in our case is also the output resistance. So now you might be wondering, how do you pick the best approach for finding RTH? And unfortunately, there's no easy answer for that. All three methods will work. It's just that normally one is easier than the other two. I usually start by trying the short circuit method, and if that seems to be intractably difficult, then I'll try either a voltage test source or a current test source. Hopefully the first approach that you pick will be the easiest, but if not, well, you've got the other two to try. All right, so we're going to go with the short circuit approach first. So coming over to the next slide, we've got our AC equivalent with RL removed. Remember, when we apply Thevenin's theorem, we remove the load. Coming over here, I'm going to start by determining VOC, and the first step there is doing KVL around this left-hand loop clockwise, and that gives me 0 equals Vin minus VGS minus V sub OC, which is GM times VGS times RS. Now I'm going to be solving this for VGS, so the next thing I'm going to do is factor VGS out of these right-hand two terms, and that gives me Vn minus VGS times 1 plus GM times RS. Again, solving for VGS, we get VGS equals Vin divided by 1 plus GM times RS. And this 1 plus GM RS pops up all the time when you're analyzing FET circuits. All right, now coming over here to the circuit, remember VOC is equal to GM VGS times RS. Let me write that. V sub OC equals GM VGS times RS. And what I'm going to do now is substitute this version of VGS into this equation, and that gives me VOC equals Vin times GM times RS divided by 1 plus GM times RS. Okay, and remember V sub OC is also V sub TH. Okay, now looking at this, you might notice if I move Vin outside here, I get Vin times GM RS over 1 plus GM times RS, and that's just the voltage gain equation with no load on the circuit. We just have RS instead of R prime S, and that makes sense, right? The output voltage equals Vin times AV, and we really haven't changed anything here except removing the load. So we could have saved ourselves all this work by just realizing that at the beginning, but going through it, it doesn't hurt to show the consistency that even if we don't realize that, we can still come up with the same answer. Now, I'm not going to leave you with this messy writing again. I'm going to pull up the nice version of this And let me clear my workspace quickly here. And we'll go down and grab the nice version. Let me cut this, and we'll come up here and paste it. And there we go. Now the next thing we want to do is determine the short circuit current. So that means we're going to be placing a short from the source to ground right here and determining the expression for I sub SC. All right, so let's go on over to the next page, and here's the circuit with that modification. Notice when we bypass the source resistor that VGS equals Vin, so let me note that here. VGS equals Vin, and our short circuit current is GM times VGS, so I sub SC is equal to GM times Vin. All right, now from our previous page we know that the open circuit voltage V sub OC is equal to Vin times GM times RS divided by 1 plus GM times RS. So RO, which is R sub TH, is equal to V sub OC divided by I sub SC. So here is V sub OC, Vin, GM RS divided by 1 plus GM times RS divided by this, so we're just going to multiply by the reciprocal, 1 over GM times Vin, and notice we get cancellation of GM times Vin here, and that leaves us with an output resistance equal to RS divided by 1 plus GM times RS. So that's the resistance that our load thinks it's looking back at the amplifier. Now, a lot of books will show you the resistance that you would see looking into the source terminal. We'll call that RO source. Okay, and that's equal to 1 over GM. All right, this equation is taking into account the fact that we have a source resistor present. So really, this equation is giving us RO source in parallel with RS, which is hidden in the equation for these two in parallel. And I'm going to leave that for you guys to show the equivalence here between this expression and this one. And note for future reference that when we do look into the source, we see 1 over GM. Now, I'm not going to leave you with my messy work here. Let me clear the boards, and I'll go down and pull up the nice version of this stuff because I love you guys so much. And here it is. So let me cut it from here. All right, we'll come up and paste it here, and now you've got something worthy of using for a reference. Before we move on, I want to take a look at something that's kind of counterintuitive that you may not have thought about, but let me bring in the circuit with our load resistor shown explicitly. And again, what we're calculating here is the output resistance from the perspective of RL. And when we look in here, it's easy to see that we've got RS, and when we go up this way, we've got a current source which has an internal resistance of infinity. So the result we've got really doesn't make sense intuitively. It looks like we should just see RS because this is infinite up this way. But that's one of the crazy things that happens when you have dependent sources in a circuit. You can get effective resistances that are very different than what you might normally expect, and you could even get negative resistance values. But I just wanted to emphasize that again, and we're looking at 1 over GM when we look up this direction in this circuit, and what we see here for this equation is 1 over GM in parallel with RS, and this is one form. All right, now let's just go ahead and take a look at the derivation of the output resistance. using Thevenin's theorem with a test source. Okay, so I've redrawn the circuit here again, and because we're using the test source method, we have to deactivate any independent sources in our circuit. We've only got one, that's V in. When I deactivate it, it shorts the gate directly to ground. Now, in this case, I'm going to apply a test voltage source, and I've redrawn the circuit one more time up here just to emphasize the fact that we see VGS equals negative V sub test. Okay, so let me write that down here. VGS equals negative V sub test. And now when I look at the drain current source, using this identity, I can rewrite that as negative GM times V sub test. Okay, now coming down here to the bottom of the circuit, note that the test source is directly across RS, so we can define the current through RS as V test over RS. And doing a little Kirchhoff's current law at the source node, V test over RS equals GM VGS plus I test, but we'll substitute in this identity. So what we end up with here is that V sub test divided by RS is equal to negative GM times V sub test plus I sub test. All right, now I'm going to collect the terms that contain V sub test on one side. That gives me V sub test over RS plus GM V test equals I test. Going to factor V sub test out of these two terms, so we get V sub test times 1 over RS plus GM equals I test. And we're almost there. Remember, the output resistance is V test over I test, so if we rearrange this equation, we get R out equals 1 over RS plus GM. And there's our output resistance. Now note, this looks a little different than when we got the last time, but if we clear the fractions here, that is, we'll combine these over a common denominator of RS, multiplied by the reciprocal of the fraction, we're going to get the same result we got previously. All right, now I did an alternative derivation of this thing, and I'm going to bring that derivation up here for you. And remember, every time I do a relatively complicated circuit, I do a little bit differently, so this is no exception. And here's what I got using a slightly different approach, but in the end it works out to be the same. I carried it a little further by clearing fractions, and what I'd like you guys to do is repeat this derivation using a test current source. In the end, you'll come out with the same answer, but the intermediate steps might be a little bit different, and it's kind of an interesting exercise. All right, now we've done a lot of work deriving all these analysis equations, and I would just like to show you some experimental results that verify all this hard work. I built a source follower using a DN2535. We looked at this depletion mode MOSFET in the last video, so if you want to know how to calculate all of these DC values, go back to the previous video and all the details are there. But in any case, the theoretical analysis for this circuit gives us an IDQ of about 5 milliamps, VDSQ 6.2, VGS negative 2.8 volts, and transconductance of about 18.8 millimos. Now, the no-load voltage gain, theoretically, that is with no resistance over here to the right of C2, is 0.9. The output resistance looking into the source terminal, RO source, should be about 53 ohms, and the overall output resistance, that is RO source in parallel with RS, should be about 48 ohms. All right, I built the circuit. All my DC measurements came out pretty much right on the money. So I adjusted V in to 500 millivolts peak to peak, and I measured V out with no load as 490 millivolts peak to peak. So the gain came out right on the money at 0.9. Then I connected this 100 ohm potentiometer to the output and adjusted it until my output voltage dropped to 1/2 of the no load value. And pulled the pot out, measured the resistance, and I came out with an output resistance of 30 ohms. So that's a little bit lower. Well, in fact, it's substantially lower than what we calculated here, but that's a good thing. The lower the output resistance, the better. So what's throwing it off probably is my estimate of some of these parameters. They're not exactly perfect. So, we're going to have a little bit of variance, but this is right in the ballpark, and it's really good. Now, before we leave, the last thing I'd like to mention is that normally the main application for source followers is in push-pull class AB amplifier applications. But this video is already long enough. I don't want to go into the weeds with that stuff now, so we'll hit that some other time in the future. But for now, I'm going to wrap it up, and I hope this was a fairly enjoyable video, and I'll see you guys the next time.